All right, so we'll finish with the last session of the day. Definitely one of my favorites because we get to talk about some of the really good details here into optimizations and things like that. If you guys need a book for Paul's walking around, you guys can grab a copy of the slides. I know we were short on one or two. I'll send my marketing person an email tonight, see if she can get printed some locally, and I'll try to bring them to our booth. So if you didn't get a copy of one or two, I know we already have extras of 3, so that's fine. But if you didn't get a copy of 1 or 2, please try to stop by the booth, and I'll send her a note tonight and hopefully have those for the exhibition hours tomorrow. If you want the exercises or anything that we're doing here, drop me an email. My business cards are right up at the front corner right here. On some of the slide decks, they have my contact information. Some they seem to have gotten deleted, but just send me an email. They're only 80 kilobytes, so as long as you can get zip files or whatever, that's fine. But so my cards are up front there too. So, and if you can ask questions after today, I'll hang out for a bit and we can chat. And feel free to stop by the booth anytime the rest of the week, and we'll do that as well. I think from admin notes, you're supposed to turn off your cell phones, they say. Again, whatever. And they want you to fill out the surveys for, I don't know, for whatever reason. So, fill out the surveys and do that as well. All right, so without any further ado, again, Paul's handing out some slides there at the back, so that's great. And here we go, Introduction to Optimizations and Profiling. This is, when we actually do this as a training course, we divide it kind of into 3 full sections, actually. We do arithmetic, like, as a whole standalone section. We do the occupancy and warps, and we do the memory also as 3 separate lectures almost over the course of a day, so we really get to dive into that. We have an hour, so yay, we'll do our best, but it'll at least give you guys an idea, and if you've had some experience with it, you'll hopefully get some other information there. We'll also talk a little bit about multi-GPUs and OpenGL interoperability, and by a little bit, there's a slide with a little bit of text on them, so there's not too much that we get a chance to talk about there. We'll do some memory performance optimizations and get a chance to use the profiler as well. Again, I'm not necessarily trying to demo the profiler. Again, there's some good sessions that are going to do that, but we will use the profiler to show the performance gain that we get by doing the memory optimization. So again, my thought process is I'm an engineer, software developer like you. I need to make my stuff go faster. How is the profiler going to help me versus, these are all the features of the profiler. That's not why I'm here. So, all right. Oh, yeah, again, you guys have seen this all day today. That's Tamara. She's our accountant. We did this again. We teach courses. We also do training and consulting, so you can come talk to us at the booth if you need some help with the CUDA application. Again, we've got people who have been experienced for this forever. Fun stuff. We were doing this with OpenGL way back when we first started. It was all OpenGL work. NVIDIA got wind of us, and they actually helped us get going way back in 05 and things like that. We ship products as well. These are standalone libraries that do electromagnetics, so finite difference time domain stuff, reverse time migration if you're doing oil and gas. We also have a biomedical imaging product using Feldkamp reconstructions and things like that. We also do training and services as well. So, I'd love to see you at one of our training courses. That'd be great. That's all in CUDA, OpenCL, and C++ AMP as well. Training schedule is posted online, so you can see where we're doing it. We also come on site if you want us to help you at your company. Time to talk about those if statements and things that make your GPU go stall and things that are not good. So a stall on the GPU occurs when your processor cannot execute the next instruction due to a dependency on the previous instruction. And this is a perfect example. So you've got some sort of kernel here. You're reading this information in from memory into this float temp. The problem is this is doing a memory request behind the scenes. So the GPU now has to issue a request out to memory, grab that information, store it in variable temp before it can do an accumulation into sum. And that's causing a stall. The GPU cannot proceed until that memory has been retrieved. How do we do this on the CPU? Main memory, regardless of whether you're on the GPU or CPU, is relatively slow. And what Intel does is they've done a really good job of trying to, as programmers, mask what's actually happening. So they build all these layers of cache that are trying to store values on chip so that the latency between when you issue a memory request to when it actually appears into the register is low. So again, if you're in an L1 cache, you've only got 4 latencies of clock cycle versus L3, which is further out. And of course, the closer you are to the hardware, the smaller the size. You know, you've only got 32 kilobytes there versus 8 megabytes there. Intel goes even further, and they do all sorts of neat things like hardware prefetching. So it attempts to move data into cache before it's requested. It'll try to execute instructions out of order if it can, and it uses something called hyperthreading to interleave instructions from independent threads. So this is how the CPU tries to work its magic. I don't want to say to let us be bad software engineers, but to some extent it's really trying to hide a lot of the nasty details about the architecture abstracted from you. And they've done a good job of that. Whereas in the GPU, previously this is about 107 clock cycles, worst case 107, but you take a look and the memory latency is about 400 to 800 clock cycles. So it's actually quite a bit larger to get memory or data from memory to the GPU. And compared to some of the CPU caches, they're relatively small. You're looking at kilobytes in terms of their sizes. So the GPU uses a different strategy to deal with memory latency. It has a different mechanism for solving this latency issue. But we need to understand it so that we can take advantage of it. So what do we do to hide the latency in the GPUs? We try to execute many threads on a given core. So what I'm trying to say by that is if you can fill the GPU with a bunch of work or a bunch of different threads, presumably while one is stalled, another one can be inserted and into the processor and actually execute without any stalls. And in the data parallel model, that works very well because you can execute threads from different blocks, for example, without any issues. And even within a block, it's okay unless you have async threads. But even in a block, otherwise you could march through your code. And that way you can always keep the GPU busy. And that's today's game, or at least this session's game. Let's keep the GPU busy to maximize this massive power that the GPU has available. All right, you guys are experts at this. We have threads that are allocated in blocks, and the blocks are then allocated into a grid. And these blocks are distributed amongst streaming multiprocessors in a way that we have no control over. A multiprocessor can execute multiple blocks, and the blocks must be independent. Now, one question that I think somebody asked me, maybe not in the lecture, but they said, "Okay, Chris, excuse me." They said there's 1,024 threads. 1,024 threads in the blocks, but my multiprocessor only has 32 cores. So how does that all work? And that's sort of what comes up now, which is the topic of a warp. So the streaming multiprocessor creates small parcels of these blocks called warps. And in the current GPU configuration, a warp is 32 threads. Warp size, interestingly enough, is a variable that you can use in your kernel if you so choose. It's defined. It's a read-only variable like blockdim. Individual threads inside a warp will all execute the same instruction until you hit a branch, if you branch inside a warp, and at which point they're free to execute independently. Again, there's performance implications. And when a multiprocessor is given one, and I put it in italics, or more thread blocks to execute, it's going to split them up into these small warp parcels, and it's going to execute them to be scheduled by the streaming multiprocessor. The threads are divided into these warps by their global index. So you're guaranteed on this ordering, warp 0 being defined as threads 0 through 31 of a block, threads 32 through 63 being warp 1. And if you have a multiple dimension, the convention is to use X as the first dimension for partitioning the warps. So warps from the same block, they can always execute independently. So there's no reason we couldn't run warp 2 before warp 0 unless you have async threads, because remember, sync threads happens at a block level. But warps from different blocks are always completely independent, so you can always interleave the gray blocks with the orange blocks because they're at the block level they're independent. And this is an important slide here, and this is the magic of the GPU. What happens when you allocate your thread blocks and your grid is that the GPU takes a look at it and it allocates the resources that it has available to as many threads as possible. And what I'm trying to say here is, if you don't have resources scheduled to you as a block, you're not scheduled to run. It's not like the CPU that's potentially going to back up registers or anything like that. It allocates it on an exclusive basis, meaning your thread will have its registers that it needs, and your block will have its shared memory that it needs. If there is insufficient, it will not be scheduled to be run. And that's the magic, because this allows you to do zero overhead switching between warps, because you don't need to back up any data or do any pipeline backing up or anything like that. If you don't have resources, you're not scheduled to run. And that's where the trade-offs are going to start to come in. So what that means is that a streaming multiprocessor can grab any warp that's available to be executed that isn't stalled. And by stalled, I mean waiting for memory or having some sort of register dependency. So warp 8, instruction 11, boom, is scheduled to run. It's had its data. It's ready to go. It can run. Notice I'm grabbing from warp 1, instruction 42. Maybe from the same block, maybe not from the same block. But what will happen is you're allowed to run these warps. It will be guaranteed to run in order. They will never run instruction 12 before instruction 11. But they might be at different parts of the code. Your first warps might be at the beginning, and your later warps might be at the end already. Again, you have no control over that, but the independence allows you to do that. These instructions are executed by the processors on the streaming multiprocessor, 32 cores for Fermi. So I'm lying to you a little bit, but it's effectively one instruction per cycle. Because they use two scoreboards, it actually ends up being 2 instructions per 2 cycles, but it effectively, the throughput ends up being 1 instruction per cycle. This is the Fermi streaming multiprocessor architecture. I don't want to highlight too much, except that there's 32 cores here. There's 2 warp schedulers, and on the right-hand side here are these FUs. That stands for a special function unit. That's the things that's doing your sines and cosines and hardware math if you're choosing to do that. It's also got 2 warp schedulers. The next one is the Kepler. Hey, the density is good because that means we have more processing power. Yay. It's also got a lot more special function units, and it's got 4 warp schedulers. You might want to update your slide deck. There was a typo in it. It says a total of 64 cores per streaming multiprocessor in your slide deck. It's actually 192. There was a transposition error there. So anyway, it's 192 is the correct number. It's correct here on my big screen. So we'll talk a little bit about some of the hardware limits. So this is an interesting trade-off that you're going to have to make, because the idea is you want to keep the GPU as full as possible, but you're going to be restricted. So interestingly enough, one of the most restrictive things ends up being registers. And you might look at these numbers and say, well, Chris, how's that possible? Like 32,000 registers? Like I said int index, that's a register. That's 1. Okay, so I have 32,767. Yeah, but it's not quite that simple. So what you'll do when you compile, let's say I have a very basic kernel. And my very basic kernel might be, let's say it uses 40 registers, let's say. Okay, so that's fine. So now I launch a thread block of 1,024 threads. So 40 registers times 1,024, I'm already at 40,000 registers, and I only have 1 thread block on my GPU. Now this is per streaming multiprocessor, so in a Tesla C2070, you got or 2090 M2090, you've got 16 of those. That's fine, but you want to make sure you can use as many registers as possible. So you can see that, boy, even 40 registers per thread, and that isn't a lot. If you call sine or cosine, you're probably already using 20 just by default. So, so you're starting to burn through registers pretty quickly. However, because you don't want stalls, you want more blocks on the GPU. So you're trading off how many registers can you use for how many blocks are on a GPU. Oh, well, that's easy, Chris. I know there's something called the maximum register count. I can just set that. Sure you can, but then you start to spill into local memory, and that's slower, so that's no good either. So like all good engineers and software computer scientists in this room, it's all about the trade-offs, right? It's all about finding that magic sweet spot of allocating as much as you possibly can to keep the GPU as full as possible so that it always has something to execute, but reducing the amount of resources you need to do it. But that's why we do what we do, right? Okay, so the maximum active warps per streaming multiprocessor, that's this number here. I don't actually think the slide deck talks about it, but this is the denominator of the fraction which they call occupancy. Occupancy is simply a percentage. So for example, if I was running I was able to get 24 warps on my streaming multiprocessor, I would have 50% occupancy. Now you might say, I want 100% occupancy. Yeah, you probably do actually, but we'll talk about that in the next couple slides. So the idea being that you want to get as close to this 48 as you can to kind of maximize your throughput of the GPU so that you can eliminate the GPU from stalling. Always keep the GPU busy. And how do we do this? I'm sort of stole this slide. Basically, we're switching other warps to mask the latency. There's two types of latencies that you're going to have to deal with. One is on chip, that's a register latency, and the other is a memory bandwidth latency. The memory bandwidth one obviously being the bigger of the two. What we actually did here, this was a fun little experiment. I'm sure I did this on Friday night because I have nothing better to do on Friday nights other than write code for the GPU. But anyway, we did this, and here's the occupancy down here. And what we actually did, I'm not necessarily showing you the math per se, but at 50% occupancy, let's look at the Tesla M2090 line. It turns out that register dependency, let's see if my math is correct, I think it's correct. After you write to a register, you have to wait 24 cycles before you can use that register value. So what that means, if you have to wait 24 cycles, that means that you need to have at least 24 things in your queue, right? Because if you could run 24 things in your queue, then by the time that 24th one is done, your value would be ready to go. So 24 out of 48 is 50%. And that's actually where you start to get full gigaflop throughput. On a C1060 and a C870, the clock counts are different. You need about 18 warps to hide the latency. And, sorry, not 18 warps. It's less than that, obviously, because it's a lower percentage. I don't have the numbers memorized off the top of my head. But yeah, it's a slightly lower number of warps that you need active so that you can hide the register latency. So this is an on-chip thing. This has nothing to do with memory yet. But oh, has it? I'm sorry. There was a change. I'm sorry. Thank you. Yes, thank you for pointing that out. There, I think in the book we have a 2050. I think it's true for the 2050. So there's no that's true. We just updated it so that we could put the 2090 on it. There's nothing wrong with the slide. It just doesn't have the 2090. Sorry, we updated that late. So yeah, if you want to sketch that in or whatever, you're more than welcome to do that. But yes, the 2050, it has exactly similar behavior. The graph is 100% correct. Yeah. It's just a different hardware card that we plotted. With memory bandwidth, it's a little bit different. With memory bandwidth, the key is you want to saturate the bus. It's going to be pretty hard to hide those 800 cycles. So what you need to do is you always want to be issuing enough of a request so that you're using the memory bandwidth to its maximum capacity. You want to be full in terms of gigabytes per second, in terms of the information that you're dragging from global memory to the GPU. And this is on a C2070. And again, what you can see here is that the occupancy, you really want to be close to 100 to be maximizing it. You probably maybe remember what I talked about this morning about those different data types. This is where that can be a little bit of advantage because 16 bytes per thread can be achieved by, say, for example, using a float 4 instead of just a float, which is 4 bytes per thread. So if you bring in a little more information per thread, you can saturate the memory bus without having to have full occupancy potentially as well. So that's a nice little bit of a feature to have there. Obviously, if you're using a double, that's 8 bytes, so it's a little bit easier. You don't quite need 100% occupancy. It's tough to get 100% occupancy without spilling heavily into local memory. I guess I should say it's easy to get into 100% occupancy, but then your local memory ends up dominating because you're reading and writing what would normally be in registers from global memory. We talked about this a little bit because you guys were very interested in this, and I'm glad you guys asked those questions. This is actually where we kind of give the full picture of this. So a warp is going to execute one instruction at a time, and full efficiency of a warp is realized when all threads in that warp agree on their execution path. This sample code is not, because you're basically saying if I'm even or odd. If I'm odd, I'm doing the top one. If I'm even, I'm doing the bottom one. If the threads diverge, the warp is going to serially execute each branch path. So only the active threads in the warp, the odd threads, are going to execute this instruction. Then you're going to execute the even instructions here. That means your GPU, again, is underutilized. You're not taking full advantage of it. In the extreme case, you did a switch on the thread ID and had 32 separate tasks. That would be the worst possible performing case. If somehow you can magically switch on groups of 32, you will notice no performance degradation because all 32 threads are doing the exact same thing. That's good. At a block level, of course, that implies the same thing, sort of. Given that a warp is 32 threads, also as a hint to select your block size, pick a multiple of 32 so that you're not wasting threads by having a strange block size. So multiples of 32 are your friend for block sizes. Strangely enough, again, if you get too big, you're not getting enough blocks. But if you get too small, you'll hit the maximum block count. So magic numbers that are awesome to try are 128, 256, 192 is surprisingly good. 384 is also surprisingly good. Those are good block sizes to kind of choose. So, sorry, I digress a little bit about this. But okay, so we're back to here. And what this slide is actually showing is if the blue is kind of executed in common, and then arbitrarily they're picking evaluation conditions here. The T's mean, for whatever reason, this evaluated to true. The F's mean false. What is basically happening here is these three instructions are orange, but then it has to do the else, and then they reconverge back together. So I'm hoping this picture answers some of the questions you guys had from earlier in the day as well about how branching occurs. But you'll notice it reconverges, if you will, after the if statement. So it's not like, oh, I branched at the beginning of my code, I'm screwed forever. No. The threads come back together as a warp, and then they continue to march down after the if statement in lockstep. This is probably, in terms of performance, the most important lesson I'll give you guys today. And again, I know some of you were asking me about this. If you guys were to send me your code and I were to look at your code, this would be what I would look for first. So reciprocally, you should, well, you guys are probably smarter than me, so maybe you know what to look for first, but at least this is what I would look for first, and this is my hint to you. Memory access patterns are absolutely fundamental and critical for performance in CUDA and on the GPU. And you're going to want to access your memory in a way that's called coalesced, and that comes up in the next slide. So as a simple example, compare this. We're doing memory accesses, and all we've done is we've basically swapped the row and column between these two. If we access it across the column this way, sideways, versus vertically, the memory access might be 1.69 milliseconds. But if we access it down the row, it's actually quite atrociously slow in comparison. And same thing with the Intel. It's not like Intel's exempt from it either. Now its caching mechanisms and its lower latency is helping out here. So the penalty isn't as severe. But what you can actually see is actually potentially you could get worse performance on the GPU if you're using bad memory access patterns. And we don't want that. So I'm going to tell you how to access memory properly is the whole idea. And when you do, check it out. Now you start to get really nice multipliers, and the power of the GPU really comes into effect here. So, I just basically said this slide. So, but bad access patterns can potentially make the GPU worse than the CPU, potentially. You know I love this picture. I'm glad it's up here again just for reference in case you didn't get it the first time. Again, we've got specific memory locations, and we're going to try to use the appropriate ones. Global memory is most efficient when the threads access adjacent elements in memory, okay? Or a contiguous aligned region of memory. That's when you get the best performance. Because what ends up happening is the GPU is going to bring in a block of data. And if each thread is using every element of that block, you have full memory efficiency. You're bringing in one element for every, you're using one element for every element you're bringing in. Otherwise, the transaction can be quite inefficient because if you're only going to use one element of that block that you're bringing in, it's a waste. You might be throwing the other ones. They might get cached. Well, sorry, they will get cached. It's just a question of are you going to use that cache before it gets eliminated. The rules for this are quite complicated, and we don't do them here. If you come visit us at our course, we'll tell you all the gory details. But in general, you actually want to access contiguously. So consider this. So in this one, it's contiguous because I'm accessing it by thread index. So every global memory address is executed. This is element 0, 1, 2, across. Whereas in this one, I'm striding by multiples of 16. Now, the GPU, though, is going to bring in this first row regardless. It's bringing it into the GPU. So we want our memory access patterns to take advantage of that. This is another one that I get when I field requests from potential customers who are interested. Your code almost invariably has some sort of data structure. Whether it's a structure or an object, a class of some description, you probably have some sort of memory data structure with some contents. Now, people will ask me, okay, what's wrong with this? I have a global index. Every thread is accessing an adjacent element. Like, it goes through 0, 1, 2, 3. I'm not scaling it by anything. Global index was our simple block index calculation. But the real problem is this. The way that structures are laid out in memory is that they populate the structure and then start the next structure. So my simple code back here, which is accessing element A1, is actually scattered quite a bit in space. It's not actually adjacent. All the A1s are not co-located next to one another. And because of that, this memory access pattern, which looks quite innocuous, is actually quite atrocious in terms of performance. So what that means is it's some sort of efficiency of, say, 8.3%. And what that means is that you might need to reconsider your design. So instead of using an array of structures, you might need to consider using a structure of arrays instead. So what I'm saying there is you have a structure of like a pointer to A1 inside your structure that has an array that's physically co-located next to one another, and then B1. Does it require rewriting some stuff? Yeah, sometimes it does, right? But in terms of performance, simply put, this just isn't going to perform particularly well. Now, granted, you'll probably use A2 later, so yeah, maybe you get some caching benefit from that. But in terms of actually taking full advantage of your memory bandwidth, you do want elements to be co-located in memory so that when you drag in a block of memory, your threads are using an element of that. I promised some real-life examples. This one isn't in your slide deck, and I'm actually really sorry about that one. But this is just something that I've seen throughout my 8 years or whatever at Acceleware, and just talking about performance in general. So I'm kind of leaving the technical stuff, just telling you some stories of things. We started in finite difference, like I say. We were doing antenna design modeling. Most cell phones are actually, or have used code that we have written at some point actually to model antennas. What this slide is really representing is an Amdahl's law kind of thing. And why it's important is it's really important you understand your code to know where the bottleneck is. Because it can actually make a serious impact on it. So antenna design is great because 95% of the runtime is actually in the solver, not too much in setup. So in theory, if you could erase the solver, you could get a 20x speed up. Now, we were actually able in the parallelism to get 35x or whatever, which means that the actual speed up is about 13 times. The reservoir simulation that we were looking at one point, it actually had a ton of setup, and the solver only occupied 40%. Now, you can see that the multipliers aren't nearly, I mean, they can't be any better than that. We did a good job. We had to work hard. We got our 5x, and we ended up with 1.47x. Now, that's all right, though, because, you know, that simulation might run 3 weeks, right? So, hey, you can cut it down by days, right? And that actually is meaningful. So that's good, too. We had a lovely story on the image sensor side. They were modeling image sensors for digital cameras. So it's a photonics thing. You got glass and silicon and all that jazz. The solver took 99% of the time, and we were able to really optimize it relative to the CPU, so very nice multipliers there. Mechanical solver, again, it's a tougher number to multiply against, but multiples of 2.5 are quite attractive. So I guess the big message here, though, is, you know, understand your problem. Where's your bottleneck? And, you know, what are you going to get out of it if you spend the time to do it? So that's some examples of things that I've personally seen in industry, and yeah, it's actually been a lot of fun. It's been a good ride that way too. So, just a couple more slides. Just in general, multi-GPU. I don't really talk about this. We talk about this a little bit more when, like I say, in the course. But you can distribute large problems across multiple GPUs. So, definitely in the reverse time migration, they're shooting seismic data. That's huge volumes of data. 6 gigabytes just doesn't cut it. You need to split it across multiple GPUs. You have to take into account a lot more system kind of level programming at that point, and it's a lot of fun actually, and it's pretty good. So within GPUs, you actually get n times the global memory and n times the memory bandwidth, obviously n times the compute power, and depending on the system, you can even get more PCI Express bandwidth too. Some of the issues, of course, is that some problems you can't partition. For example, sparse matrix, you might still need a full copy on each GPU, and you also have to synchronize another level. Sometimes you have to exchange from GPU to GPU. You can do some pretty clever things, though, where you actually do the transfer from GPU to GPU while you're continuing to compute to hide that latency as well. And it's, again, a bit of a challenge, but it can definitely get you to another level of performance also. So there's definitely some things to consider. To program multi-GPU, I think we have actually a slide here. NVIDIA's done a fantastic job of making this very accessible. Prior to this, when we were first starting out, you really had to work to make multi-GPUs happen. Not so anymore. It's very straightforward. You can just query the number of devices in your system. You get the number of GPUs back. This is obviously doing nothing intelligent, but it's basically looping over all the GPUs. CUDA set device tells you which GPU all following CUDA code is going to target. So it starts off by targeting GPU 0. It allocates memory on GPU 0, launches on kernel GPU 0, resets it for some reason. Like I say, it wasn't an intelligent example. And then we move to GPU number 1, and then we would repeat with that process. But it lets you access multiple GPUs within the same thread. You're also, of course, allowed to use multiple threads to access multiple GPUs as well. You can just control it by which one you want to target as well. A little bit about OpenGL interoperability. Not a world I'm particularly familiar with, but there's some really cool things that people are doing here, and I just want to share with you. And I've got a chance to talk to some of the customers who are doing these kind of things. What they're doing is, let's say you've done some really good work with CUDA, or you've done some math there, and you need to visualize it. This is where interoperability with OpenGL or Direct 3D is excellent. You can read and write the same CUDA memory that you've done your calculation on without having to transfer it back to the CPU. So you don't actually have to bring it back and forth across the bus. It can still stay resident on the GPU, and you can use it. So that's good. So I mean, these are probably contrived examples, but yeah, you've got vertex and image data generated with CUDA. Then you render it with OpenGL. You don't need to bring that data across the bus. You can call some OpenGL functionality that will allow you to exchange that information. And then vice versa, render an image with OpenGL in post-process. But you guys probably have much better examples than this. So tell me so I can use them later. So yeah, go ahead. Sorry, the question was, can this be combined with the host and device memory mapping? This is exclusively on device right now. That's the idea. That being said, there are ways you can communicate with the host directly from the device using pinned memory and something called zero copy. You can definitely do that, but we'll take that one offline and we can chat about that after. I think I'm going to take that one offline because it's a little bit more complicated. You have to do some things to set it up. The premise of zero copy, just as a high level, is that it'll allow you to not have to actually declare memory on the GPU, and it directly goes into from the host to the device, and it implicitly transfers it. It's actually very quick to bring it across the PCI Express bus. The limitation is if you're using the data more than once, it's going to go back and forth across the bus. So you have to have a very particular application that you'd want to do it for, and the reason you want to do that. But we can chat a little bit more about that after, and if you have an application you're interested in. All right, so the Visual Profiler. Again, I'm going to show you an example of some code. Again, I'm showing the profiler, not trying to advertise it or show it properly. Again, there's good people to do that. But what it will show, which is pretty cool, is it will show some issues with some existing code that we have that should hopefully trigger back to this lecture, and maybe we can think about ways that we can improve our code, and that's the reason we're going to really be using the profiler here. It's a really nice tool. It's a really nice tool. It's supported on all flavors of OS, more or less. Works in Linux, works on Mac and Windows. You pretty much just select your input argument, generates a really nice timeline, and you'll see that when I demo it, and then you'll run it. So in terms of a demo, it's not going to be, again, particularly exciting. We're just going to scale a matrix. We'll do it in place. Y and X are two-dimensional square matrices. And yeah, we'll go from there. So we'll do that. Okay. All right. Which one is this? Close this up. All right, so we have our exercise. I'll take you through it. It might be a little bit more. Yeah, you got a few more files in here, which is all right. Fairly, I guess, reasonably large block size here. Again, we're just randomly going to fill it. We're going to compare it. We have a reference solution on the CPU that we're going to compare against, and then we're going to scale it by calling the kernel right there. The kernel itself actually has a device function, which is kind of nice as well. So this is the entry point. Global is the entry point. It's going to enter here, and it's actually going to call this device function with an offset into the array so that it keeps it fairly small here. And we're just going to do our scaling. Sorry, and I'll make the code bigger. I'm sorry, guys. We'll do the scaling right there. Okay, so the first thing I want to do is I want to run it and make sure that my arrays match, which I'm hoping they do. Okay, so the arrays match, so that's good. So we've got that. And okay, so this is I'll close this too. This is all good. And now what we'll do is we'll open up the profiler. This is all this. Most of the things that I'm showing you here actually are you just download from NVIDIA's website. They provide these tools for all of us to use. So this is good. So when you install the toolkit, the Visual Profiler is installed as well. Yeah, so I'm not doing anything fancy here. It's just it comes with the toolkit that you get when you install the compiler. So we'll open the profiler and we'll see how our code looks. So first thing we'll do is we'll create a new session, and it's very simple. We'll just browse to the appropriate location. So I was in the working exercises. Just needs to take the executable. You can enter your working directory in some command line arguments if you need to. We won't because ours is simple. And if you have a timeout, you can do that too. And then we're going to run the analysis. So it's going to start and it's going to generate some nice results for us here. So I'll take you through some of this. I guess I'll even highlight that for now and just jump down. So some things that it's going to show us. Over in that column right there, it's telling us how long it took to do the host-to-device copy in milliseconds there. And then it's telling us how long our kernel took to run, which is this blue bar right here. We didn't really talk about streams, but you can run multiple streams on the GPU if you want to interleave your communication and computation. But this section here is showing the runtime of the kernel. Now, I've highlighted it. It gives us a bunch of details. It tells us that it takes us 416 milliseconds. Our grid size was 25 by 25, and we launched it with 192 log sizes. Only 8 registers per thread, which allows us to get to 100% occupancy, actually. So that's pretty good that we can get that high. But the 8's a really low number. In practice, you're going to have a number much higher than 8. That's because this example is actually fairly simple. All right, so running back here, and what I want to show here is I'm just going to reset all of these, and I'm going to do an analyze all down here, and it's going to take us through all the things. It needs to run. Oops, sorry guys, just popped off here. That's okay. That was a good distraction because it still needs to run 15 more times to do this. So, and then what it's doing is it's collecting counters on the streaming multiprocessor, and it's going to display it. So it's testing different things and just recording information that it's going to display. And what's going to happen is it's going to tell us that we didn't do a good job in some things and other things are fine. So, okay. So it's complete. So for example, it highlights here we have a low mem copy to compute overlap. So we're not interleaving any of the compute with mem copy. So it's warning us that maybe you could do that. Maybe you could try to interleave communication with computation. Now, obviously, this is a simple example, so it's not so exciting. Yay, we did good there. But what we didn't do good on was it said it was low global memory load efficiency, 3.1% average. Global memory loads may have a poor access pattern. So it's hinting to us that we are not doing a good job of our memory. Like I say, if you guys were to give me code, this would be the thing that I would be looking for, is this, okay? Because this is going to make a big difference in our code. And in fact, it's saying that there's a high instruction replay overhead, meaning that non-coalesced global memory accesses are causing significant instruction overhead. It's telling us that we are not accessing our global memory in an efficient, coalesced way. Oh, okay. So better go take a look at the code and see where we're failing. You know, why aren't we doing a good job? So it has to do with these lines right here. Again, they look fairly innocuous, but upon further investigation, you can see that we're actually scaling the thread index by the size that we're passing in, meaning that it is striding. Those threads are being scattered throughout memory. They're not contiguous anymore. They're not accessing adjacent memory elements. In general, don't do this. Don't scale your thread index. That's a bad thing typically. So what we're going to do is simply just swap I and thread index. And obviously this is a contrived example, because if we could all do this with our code, it would be really easy, right? So thread index dot x plus I, plus 1. Okay, and then we'll just switch this here. So now instead, we're offsetting by index and we're scaling by I. But what that should do is it should allow all the elements in the, or all the threads in a warp or block to access adjacent elements. So I'm going to rebuild this, and I'm going to rerun it. Okay, let's just make sure the arrays still match and all that. Okay, so we still have correct output. I'll leave this session up. And actually, by the way, there's a console output that actually tells us that too in the profiler. It'll actually display the console output. It's a really nice tool. So we'll actually open up a new session here. It's in this, yes, I'm in the correct directory. So I'll just run this, but it's in a new session. We'll finish this. It's generating the timeline, and already if we check this out, the duration is 18 milliseconds. Oh, that's nice. Anybody from NVIDIA want to talk about that? Oops, sorry. The duration is 416 milliseconds, but check that out, right? That's a huge multiplier difference. I'm tempted to see the details. Yeah, so that's a big difference right there. 18 milliseconds versus 416, right? So memory access patterns being very, very critical for your device. Like you can see. That's why I'm looking for that first. Because if you want to get the big multipliers with your GPU, you need to worry about how you're accessing your memory. So just for fun, let's reset all this, and then we'll do the analyze all. So again, we'll have to wait while it collects all that information. But I guess while this is running, you know, sort of that message that I want to leave you with, you know, array of structures is bad. Structure of arrays is good. Be sure to access your memory with your threads in a coalesced fashion as much as possible. I understand people, I've had people talk to me and say, well, I'm doing map paths or like traveling salesman problems and stuff like that, and those aren't necessarily as well suited to that because they can potentially branch and cause non-coalescing, but when we can, we want to use that. So it's still saying we're having a low compute utilization and things like that, but that's mostly because this program is so small. If we were to expand the data, this message would go away. No issues here, no issues here, no issues here. So it's telling us that we've corrected it, and we can see it in the performance of the code that we're down to 18 milliseconds. Yeah, they give us some throughput numbers here. There's something else I wanted to do. Oh yeah, I wanted to look at this a little bit as well. So it's actually going to tell you your global load and store efficiencies of your kernel. It'll also tell you your achieved occupancy versus your theoretical occupancy as well. So again, it's a good target, so you can try to strive to get it up to 100% there. It tells you your configuration of cache and things like that. So yeah, so that's the profiler and quite good. Again, it shows us how to go. So yeah, I think just to conclude on performance, things that you're going to want to balance are your memory throughput patterns are by far the most important thing that you need to look at. After that, I want to make sure that your occupancies are really high so that you're either not using too many registers or you're using too few. I want you to get as many blocks on the GPU as possible so that you're keeping the GPU occupied and not stalling. So those are the first two things I look at in terms of performance and getting the performance out of the GPU. And those are the messages, yeah, that I would leave you with for to take home as well. So again, you guys have been awesome. Thanks so much for coming out today and listening to me drone on for that. I hope you guys got something out of it. Again, if you didn't get all the slide decks, we have extra 3s and 4s, and I'll try to get some 1s and 2s printed for the exhibition. But otherwise, yeah, stop by if you have any questions at the booth, and we're happy to answer them. I'll be hanging around as well. And drop me a line if you want these exercises or whatever. I'm happy to fire them off to you also. So thanks, everyone. Appreciate that. Thanks.